From the Earth to the Sun, 93 million miles. From our Milky Way to the other nebulae of space, millions of millions of millions of miles. And on the other hand, the diameter of the nucleus of an atom is so small that it would take several million millions of them laid end to end to make 1 inch. Well, millions of millions of millions, aren't we fooling ourselves? How can man or his instruments possibly come up with such figures? How can science take such measurements?
Well, those are fantastic figures. Millions of millions of millions. Apparently scientists here are dealing with very large and very small objects. However, very large numbers by themselves do not prove that objects are large. For example, 60 million is a large number, yet 60 million inches is only about 100 miles, not a very long distance to cover by car. A distance is not very large by itself. It is only large or small in comparison with some other distance, for instance, an inch or a mile. These are units of distance or length. Well, the same thing is true of all the other quantities which we consider in physics. A certain weight, for example, will be expressed by a very large number if we use the grain as a unit of weight. Let's say an object weighs 14 million grains. Actually, this is only 1 short ton, 2,000 pounds. And that's a very small quantity with regard to the weight of water displaced by an ocean liner. You see, our fundamental units are measurements at our scale, at man's scale. The foot, the pound, the second. Originally, the standard of length was the length of the king's foot. The pound, a very ancient unit, has no such immediate reference to man's size, but it is a convenient weight for any man to carry. The scientific unit of time is the second, and this is very nearly 1 beat of our pulse. If necessary, we use multiples of these units, such as the mile, the ton, the hour, or submultiples, like the inch or the grain. In this way, things large or small are always, in the last analysis, referred to something definite at man's scale. So, with this human scale in mind, it makes very good sense to say that the Earth is something very large with regard to us, or that a protein molecule or a virus is very small. Neither of these is really so large or so small as to be unimaginable, but beyond the size of the Earth and the size of the virus are unimaginable distances in space and the incomprehensibly small weight of the electron. The sizes of these may be described as unimaginable, but nevertheless the scientist can measure them. I'd like to suggest to you how this is done. And in so doing, I'd like to point out that these measurements are not taken without good reason. The reason lies in the effects produced by recent discoveries in science. In the 19th century, scientists may well have found out almost about things at our scale, at man's scale, have to contribute. But around 1900, those scientists discovered a revolution in science, which is still far from having run its course. Scientists started discovering that objects incredibly small, the atom, and below the atom, the electron, vibrations incredibly fast, temperatures incredibly low, behave in unexpected ways. And perhaps these hold the key to the architecture of the physical universe. The secret may lie in a better understanding of cosmic particles, of chromosomes or genes, or events in nebulae far away in space. In our understanding of the very large and the very small, may well be the difference between life today and life 50 years hence. So these very large and very small measurements are important, a fundamental part in the advance of science. How do we get at them? With this, a yardstick will do to measure length at the scale of our body. In assisting science to measure something as large as the size of the Earth, it really won't do. It's almost as if you were to use this to build a modern superhighway. It simply is not able to deal with a job of that size. Centuries ago, this flint was capable of dealing with the scraping and the chopping and the smoothing out which came the way of our earliest ancestors. It belongs to the pre-scientific world, which was adjusted to deal with things you could hold in your hand, judge with your senses, and work on directly. Rather, it is of the essence of contemporary science that it has evolved indirect methods of obtaining the size or the weight or the speed of things it talks about. Now, this is not to suggest that the senses, fundamental to direct measurements, have no part in indirect measurement. On the contrary, in the last analysis, all scientific instruments terminate in the use of the hand or eye. Instruments become extension of the senses, just as mathematics becomes an extension of simple mental arithmetic or logic. You cannot escape using your hand and your eyes, even if you are measuring things you cannot touch or see. For example, in the heart of this oil refinery, processes are going on at temperatures and pressures which no man could stand. Reactions are taking place in gases which no eye could see. And yet you can read those instruments, which gives you measurements of temperature, pressure, and so forth. And by hand, you can control reactions you cannot see. In the end, ultimately, the measuring apparatus must involve pointers and scales to be read and evaluated by the eye, and switches and knobs to be manipulated by hand. From the direct measurements taken in units at our scale or close to it, there is still a very large gap to the gigantic measurements in space and the infinitesimal dimensions at the core of the atom. Science bridges the gap by indirect measurement, by evolving an appropriate theory expressed in mathematical terms. These theories are a different one for each specific case. Use the framework of mathematical formulae to connect enormous or tiny quantities with others at man's scale. These theories are usually specific applications of the laws of physics. Such theories are the key to indirect measurements. I'd like to show you an actual case of indirect measurement of an object very large at man's scale. How can we find the size of the Earth? The Earth is large, but not so terribly large. As a matter of fact, this was one of the first quantities which early scientists successfully measured. The man responsible was the Greek astronomer Eratosthenes, and he lived in Alexandria about 200 BC. To make his measurement, he first needed certain assumptions. The first of these was that the Earth was round. The Greeks knew that because in observing the sun, they knew that the sun lay higher above the horizon as they sailed or marched to the south, and lower as they traveled north. Secondly, they knew that if they divided the circumference of a circle in 360 parts or degrees, they could find the length of any portion or arc of that circle by using simple proportions. Suppose the arc is limited by an angle of 34 degrees. Then the length of arc is to the length of the circumference as 34 is to 360 degrees. In the third place, Greek geometers had evolved a formula to express the circumference of a circle, 2 pi r. R here is the initial letter of radius, pi is the initial letter of perimeter, and it stands for a definite number, 3, and a fraction. Knowing this formula, if you have a value for the radius of a circle, then you can find the circumference, and vice versa. With this information, the knowledge that the Earth was round, the perimeter of a circle, 2 pi r, and the length of an arc, Eratosthenes began his indirect measurement of the size of the Earth. For several centuries, the Egyptians had erected obelisks in their cities. Besides having religious and political significance, they were used for astronomical observations. Alexandria and Syene, a city to the south, had such obelisks. Eratosthenes knew that in Syene, the sun was exactly overhead at noon only one day in the year, the day we would call the 21st of June, the day of the summer solstice. On that day at noon, the obelisk in Syene cast no shadow in any direction. However, far to the north in Alexandria on the Mediterranean, the obelisk did throw a short shadow at noon on the 21st of June. From the length of that shadow, knowing the height of the obelisk, Eratosthenes could figure out by how many degrees the sun failed to be exactly overhead, and that was about 8 degrees, or 1/45th of a circumference of 360 degrees. Eratosthenes then drew a diagram, which must have looked exactly like this one. From this diagram, you can see that 8 degrees is also the angle which limits the arc between Syene and Alexandria. The angles on the diagrams are made much greater for better legibility. These two angles are equal because the two lines from Syene to the sun and from Alexandria to the sun are practically parallel. Eratosthenes assumed that they were, because he knew that the sun was very far away, at a distance at least hundreds of times the size of the Earth itself. And today, we know his assumption is thoroughly justified. Using the information he had about the Earth being round, the perimeter of a circle, 2 pi r, and the simple ratio of arc to circumference, Eratosthenes could state that the distance from Syene to Alexandria was to the circumference of the Earth as 8 degrees was to 360 degrees, or as 1 to 45. Therefore, the circumference of the Earth was 45 times the distance from Syene to Alexandria, but it is also 2 pi r. Therefore, the radius of the Earth was 45 divided by 2 pi times the distance from Syene to Alexandria. How Eratosthenes obtained the distance of Syene to Alexandria, I don't know. He probably just asked the Egyptian priests. Distance between towns were well known, and the distance from Syene to Alexandria was known to be 5,000 stadia. When we try to check this today, we fail because we don't know exactly how long a stadium was. However, if we compare it with modern measurements, we can see that Eratosthenes' result was reasonably accurate. The modern value is 4,000 miles for the radius of the Earth, or 8,000 miles for the diameter. This indirect method of measurement is quite different in its logic from common sense. Its basic is a theory which is straightforward, but which connects elements which common sense wouldn't think of connecting. The length of the shadow of the obelisk with the radius of the universe. This indirect measurement can be compared to a campaign prepared by an army commander. He, like the scientist, arranges his forces on paper first, on a field map. In the same way, the scientist plans in advance the measurement he can make directly, fits them into his formula, which expresses an approximate theory, and indirectly reaches the measurement which would have been impossible to make directly. Now, we've been talking about the measurement of the Earth's radius, 4,000 miles. Notice that this is really a very large distance at our scale. To reach a height of 4,000 miles, about 4 million men would have to stand on one another's shoulders. So this is a very large measurement. But beyond it, like much larger ones again, for instance, after we measure the radius of the Earth, we want to know the distance to the Sun. And this is quite another matter. The Sun is so very far away that instead of measuring an angle of 8 degrees, as Eratosthenes did, we would have to measure an angle 3,600 times smaller, 8 seconds. And this is much too small for direct measurement. So astronomers did not know the distance of the sun very precisely until quite recently, about 20 years ago, when they were able to find the distance to a very minute planetoid called Eros, circling between the Earth and the sun. With the help of Eros as a stepping stone, astronomical theory was able to obtain the distance to the sun, about 93 million miles. Note that we can repeat these words, 93 million miles. Write them down in a notebook for future use. But imagine that distance? Never. We are already in that realm of science where we reason, we compare, we obtain numerical answers, but we are so far from man's scale as to be much incapable to visualize what we have indirectly measured. In the same way, we go from the sun to the nearest stars, from these to the dimension of the Milky Way, from this to the distances of the nebulae. And at each step, we must invent a new theory, a theory which enables us to climb from one kind of distance to another kind, much greater. Each climb involves measuring auxiliary quantities which are at man's scale, within our reach. But once entered into the formula, they enable us to reach some hitherto unapproachable distance. So much for the very large. Now the very small. Here too, the method of science is indirect. You can measure this with a ruler. But this is another problem again. And beyond the ball bearing, how to measure what you cannot hold in your hand? A red cell of the blood, perhaps. And still something smaller than the red blood cell. How to measure the size of a virus? For the ball bearing, you can use this micrometer, more sensitive than your naked eye. When I turn this drum here, I advance a very precisely constructed screw, and when it has advanced the diameter of this ball, then I can read off the drum exactly what the diameter is to within 1,000th of an inch. For the red blood cell, however, you must first locate the object to be measured and then devise your method. Here's the solution to that problem. A microscope. To enlarge the red cell, this instrument here increases the power of your eye. Look through the eyepiece and you see this, the red blood cell. Now suppose you attach to this microscope another sort of micrometer arrangement. We have to take the ocular piece out first and we substitute this micrometer. This places a carefully built grid in your field of vision. Rotating this drum here moves a hairline across the grid. You can line up one edge of the cell with a hairline, then move the line across the cell to the other edge, and note how many divisions of the drum were needed to do this. Again, this is indirect measurement, because you see, you can't read directly the size of the cell. You have to know what fraction of an inch is represented by each division of the drum of the micrometer and how much the microscope amplified this particular measurement. The maker of the microscope provides that information by means of an extremely intricate physical theory. The magnifying power of this instrument depends upon the type of lenses the maker used in the various lenses inside of this tube, upon the distances between the lenses, the different curvatures he gave to the lens surfaces, and so on. Let's say that the distance, that the designer may tell us that the real distance between one edge of the red cell and the other are magnified 30 times at the level of this micrometer. Let's say by twisting this drum through 4 divisions, we move the hairline by 1/100th of an inch, and suppose that that moves the hairline across the red cell. Now, by magnifying the magnifying power of the lenses below this micrometer from here to here is 30. And so 30 times 100 is 3,000. Therefore, the diameter of the cell is 1/3,000th of an inch. So the measurement of the size of a red blood cell is direct in the sense that we are using our eyes to look at that cell, just as direct as looking at fine print by means of a magnifying glass. But the actual measurement is the size of the cell is very indirect. It uses elaborate formulae because it depends not only on this, the micrometer, but upon the whole design of this instrument, this microscope. Now, 30 years ago, scientists believed correctly that there was a limit to the use of optical instruments in seeing small things. Because optics is based on the controlled use of light, it was known that some particles would be too small to send light effectively back through the lenses of a microscope. Therefore, they believed that we would never be able to see objects smaller than about 1/10,000th of an inch. However, the scientists of 30 years ago did not foresee the use of a beam of electrons in place of a beam of light, and later this was realized. Just as glass lenses direct and focus light, so a stream of electron was focused by electric or magnetic lenses. Just as light could expose a photographic plate, so could electrons. With the electron microscope, we no longer look at the object itself, we look at a photograph of the object made by a stream of electrons exposing a photographic film. Or we look at a screen, like that on your TV set, energized by a stream of electrons. Here again, and now very indirectly, you can measure the dimensions of a very tiny object using the very involved formula describing the electron microscope. Here is a picture of a virus. Each of these little particles has a width of the order of 1/1,000,000th of an inch. Notice that the way you are looking at this virus is identically the manner in which you are looking at me now. You are not looking at me directly, but rather at a photograph of me made by electron streams on a photographic film. And in turn, my photographic image is translated by another beam of electrons into the image on your television screen. And yet, only a purist would want to insist, don't you think, that you are not at this moment seeing me. In the same way, the scientist commonly forgets that he's measuring the earth or the blood cell or the virus indirectly because he's so sure that he's obtaining the size of the real thing. Well, perhaps you're getting used to this indirectness of science, but you may still wonder at the large and the small of it, the huge or tiny numbers arrived at in this way. You may still wonder how, using measurement at our own scale, we produce such enormous, unimaginably large figures. I want you to notice that the common characteristic of the formulas which we use in this indirect approach of science is that they usually involve multiplication or division. Look, the distance from Sion to Alexandria divided by the circumference of the earth. 8 degrees divided by 360 degrees, 8 multiplied by 2 pi. The circumference of the earth is 45 times the distance from Sion to Alexandria. Notice the things we are working with were distance, measured in stadia, today in miles, and angles in degrees. Now we can't add or subtract quantities of different kinds, like adding distances and angles. We can only multiply or divide them. Now here's one effect of this. The radius of the earth is 4,000 miles, we said, and they are 5,280 feet in a mile. Both, you will notice, reasonable numbers into the thousands. But when we multiply them, we find that the radius of the earth in feet is 21,120,000 feet, which is an unimaginably large number. Multiplication and division are thus methods of manipulating very different sorts of quantities, degrees and miles, or volts and amperes and hours. This connecting of very different sort of things made possible by multiplication and division, is characteristic of physics and some other sciences. The significance, the power, the beauty of physics consists of just that physics connects little by little everything in the physical world: weights, distances, speeds, temperatures, calories, colors, voltages, the sun and the electron, waves and particles, everything with everything else. That is physics. And that is why physics always multiplies and divides quantities of different kinds. And incidentally, in so doing, it produces these very large and very small numbers I've been talking about. Incidentally, but not meaninglessly, because there are things in nature that are fantastically larger than man. For instance, the Milky Way. And there are things very much smaller than man, so very much smaller, say the electron. And physics is finding out about both the Milky Way and the electron. It would be untrue to say that it has connected them. It hasn't. Not yet. But several physicists have had the courage to say aloud what many others are just too shy to admit, that they believe they are connected, although they cannot prove it yet. In any case, between the very large and the very small stands man, about halfway in size. Among the dozen or so physical quantity which seem to be prominent in the physical universe, some, like the speed of light, are very large at man's scale. Others, like the energy carried by a grain of light, a photon, are very small at man's length again. So large and so small that without doubt this is the reason why it is difficult for man's imagination to invent new ways of thinking to accommodate their meaning and their implications.
This is National Educational Television.